بسم الله الرحمن الرحيم. بنرحب فيكم في المحاضرة رقم 10 في الأوبتمايزيشن تكنيكس. اليوم بدنا نكمل طبعا في الإتراتيف algorithms for optimization. راح نتكلم اليوم عن تكنيك جديد اسمه Conjugate gradients. So we are still in iterative algorithms for optimization. وحديثنا اليوم راح يكون عن تكنيك اسمه Conjugate gradients. بس حتى يعني نمهد للموضوع شوي. steepest descent التكنيك الأول اللي أخذناه. So steepest is very slow. So this is the drawback of the steepest descent. One major drawback of the Newton's method is that it requires calculation and storage of second derivatives. Especially when the number of parameters to be optimized is very large. So calculation of the Hessian is one drawback of the Newton's method. You have to find the second derivative of all parameters that you have with respect to themselves and with respect to the other parameters. So conjugate gradient does not require to calculate the Hessian matrix. Okay. All right. So let's see how things goes with the conjugate gradients. Let's do some mathematics first. Suppose that we wish to locate the minimum of the following quadratic function. So I have a quadratic function, and we'd like to find the minimum. Our function is f of x equals to 1/2 x transpose a x plus d transpose x plus a constant c. Okay, so this is our quadratic function. Definitely a is the Hessian, we know that, and d is the ax plus d is the gradient. Okay, so set of vectors p sub k is mutually conjugate. A set of vectors pk is mutually conjugate with respect to a positive definite symmetric Hessian matrix Hessian matrix A if and only. So the set of vectors pk is mutually conjugate for this matrix if and only if pk if and only if pk transpose a p sub j, okay, is equal to 0 for k not equals j. So it's some type of orthogonality actually, but it's not somehow orthogonal if you are taking pk with a as one element. Okay. As with orthogonal vectors, there are an infinite number of mutually sets of vectors that span a given n-dimensional space. Okay, so you have P1, P2 up to Pn mutually conjugate vectors. Okay. One of those sets are the eigenvectors of the matrix A. One set of conjugate vectors consists of the eigenvectors of A. if we let lambda 1, lambda 2 up to lambda sub n and z1, z2 up to z sub n be the eigenvalues and the eigenvectors of the Hessian matrix A respectively. What we mean by that, lambdas are the eigenvalues and the z's are the eigenvectors of the Hessian matrix A. We can show that the eigenvectors are conjugate. Conjugate vectors. So if we replace pk with zk, then we have z sub k transpose A z sub j. This is equals to lambda j times z sub k, z sub j, z sub k transpose. So this one, those are mutually orthogonal. And this one is true because lambda I is the eigenvalue of the matrix A. So this is lambda j times zk, z transpose times z sub j. This is equals 0 for k not equals to j. So we assume that those are multiplied by each other. This is zj. Lambda j times zk transpose is equal to this one times zj, and zk with zj, they are mutually orthogonal because they are eigenvectors for a symmetric positive definite matrix. Okay, so we can take basically we can take the eigenvectors to be our p direction, but what is the problem here? The problem is that we have to calculate the Hessian matrix before we calculate the eigenvectors. So once again, the conjugate gradient method supposed to get rid or to not to take care of the Hessian. So we need to reduce the Hessian from our calculation. Okay. So the eigenvectors are both conjugate and symmetric. Sorry, conjugate and orthogonal. I'm sorry about that. Conjugate and orthogonal. Okay. But adapting the eigenvectors z sub k as search direction is not of much, it's not of much practical help. Why? Since to find the eigenvectors, we need to find the eigenvectors, we must find the Hessian matrix first. So we must first find the Hessian matrix. Okay, so this one is not of much help. We are looking for another way of or another search directions. Okay, see what we will do. If we make a sequence of exact linear searches along any set of conjugate directions, P1, P2 up to Pn, then the exact minimum of any quadratic function with n parameters will be reached at most n searches. So if we are going to do conjugate directions from P1 to Pn, those are enough to go for a quadratic function with n parameters to you go to the minimum with at most the n searches or the n directions that we already proposed here. Okay. So the question here is how to construct these conjugate search vectors. So the question is how can we construct these conjugate search directions. Okay. Okay, the first step is to restate the conjugacy condition. The conjugacy condition, which states that P sub k transpose times A P sub j equals 0 for k not equals j. So this is our condition for conjugacy. Okay. We would like to do that without, so step to restate the conjugacy condition without using or the use of the Hessian matrix. So we need to restate this conjugacy condition, but we have to get rid of A, to substitute something else for A. Okay, so recall that the quadratic function recall that for the quadratic function, the gradient of f of x, so recall that for the quadratic function, the gradient of f of x is equal to ax plus d, and the Hessian of f of x is equals to a. Okay? Now, what we are going to do, we'll do some trick here to get rid of the Hessian by taking the step of the gradients. So let's call delta g sub k is equal to the gradient of k plus 1. Okay, this is also, we call this g, the gradient, yeah? So this is the so g, which is the gradient, we take the difference of the gradient of step of k plus 1 minus g sub k. Okay? If we take this to be a x at k plus 1 plus d minus a at k times x, sorry, a at xk, x at k plus d. Okay, so d minus d is equal to 0, and you end up with a delta x at k. This is equals to delta g sub k. So delta g of k is equal to the Hessian matrix times the step in x, the difference of x, and this delta x, where delta x is equal x of k plus 1, x of k. Okay? And this is supposed to be alpha k delta x is alpha k pk. In our search direction, we know that this is the case. Okay. Now, this is your delta x at k. Yeah. And it's a vector. And it's equal to the alpha, the step size, times the direction of the search direction. Okay, a vector in the search direction, where alpha k is chosen to minimize f of x in the direction of p sub k. So if we restate, the conjugacy condition, and now we will take a delta x that we have and see what we are going to do now. Notice that alpha k pk is equal to delta x. Delta g is equal to a delta x. Okay? If we multiply both sides here by alpha k, so it still equals to 0. So we can say that this alpha k times pk transpose a pj still equals to 0 for k equals j. Now, alpha k is a constant, so alpha k pk times ak, this can be said to be equals to delta k transpose. So this is equals to delta x at k, delta xk transpose a pj equals 0. Now, if you take this here and replace it by this one here, so you will have delta g sub k transpose times pj equals 0 for k not equals j. So if you notice here, this equation here, you no longer need the Hessian to calculate the conjugacy. So we replace the Hessian by the difference of the gradients. So we replace the Hessian by the difference of the gradients. Okay. So we no longer need to know the Hessian matrix. Okay. The search directions will be conjugate if they are orthogonal to the changes in the gradient. And as you can see, this is an inner product between the changes of the gradient times the search directions, Pj, and should equal to 0 with any j not equals to k. Okay. Okay, where to start from this algorithm? We have to start from some Pj. We have to set some Pj, and then we develop the other P's. So it is common to begin the search in the steepest descent direction. That is P0, we'll take it in the minus G0. Okay, so the first direction that we are going to take, P0, is in the negative of the gradient at the initial, or the initial gradient that we have in our function. So this is our starting point. Then at each iteration, we need to construct a vector pk that is orthogonal to all the gradient differences before, delta G0, delta G1, until delta G at k minus 1. So pk is chosen such that it is orthogonal to all those previous delta G's. Okay. This can be simplified to iterations of the form P sub k is equal to minus G sub k plus B beta sub k, sorry, this is a constant, beta sub k times B sub k minus 1. Okay, so this is how we are going to reconstruct this, as if you are starting from P0 minus J0, and then for the next iterations, you're going to take this one. So if you make this one to be P1, it's at K, and this one is at P0, okay? This scalar, the scalars beta sub k can be chosen by several different methods. okay, which produce equivalent results for quadratic function. Okay. The most common choices are the first choice is beta sub k is equal to delta g of k minus 1 transpose gk over delta g sub k minus 1 transpose pk minus 1. Okay, this formula is made by Hastings and Stiefel. So this is the first choice. The second choice, beta k, is equal to gk transpose gk over gk minus 1 transpose gk minus 1. Those are vectors, inner product. Okay. And this is according to Fletcher and Reeves. And the third choice is beta k is equal to delta g k minus 1 transpose gk divided by gk minus 1 transpose gk. Okay, and this is according to Pollack and Ribery. Pollack and Ribery. So you have three choices of beta. The most common one is the second one. But all of them are applicable and they give exactly the same results or equivalent results for the quadratic functions. Okay. Now, everything now is in its place. Let's see how the conjugate gradient steps are. Conjugate gradient steps. Step number 1, we have to select the first search direction to be the negative of the gradient. Okay, so we'll choose it P0 equals minus G0. Okay. The second step is take a step according to x of k plus 1 equals x at k plus alpha pk alpha k. Where alpha k is usually selected to minimize the function along the search direction. Okay. We did this previously, and we found that alpha k equals to minus gk transpose pk over pk transpose a pk. Okay, so, but notice here that alpha k, to calculate alpha k in the search direction, we did it previously, but still we need the Hessian here. There are other iterative ways to find alpha k, and alpha k, to find alpha k without using the above formula. The golden section method is a good choice. It will be discussed later. So we'll come to this one and we will discuss it in a later, in future lectures. Okay. So now we have alpha. At the time being, we will stick with this alpha. Okay. So step number 3, we have to select the next search direction, and next is pk equals to minus gk plus beta x, or sorry, beta k p k minus 1. Okay, and we can choose beta k from one of the 3 choices. Our 3 choices. So we have 3 choices for beta. We can pick one and see what will happen. Okay. The last step, if the algorithm has not converged, return to step 2. So we go to step 2, find x of k plus 1, go to step 3, find next pk, and then check the algorithm once again for convergence. So, okay, I'm going to take an example and discuss this, or those 4 steps together with you, and see what will happen with our example. Okay. example, let f of x equals to 1/2 x transpose 2, 1, 1, 2 x with initial guess x0 equals to 0.8 minus 0.25. Okay. Now the gradient of f of x equals to, this is a symmetric positive definite matrix. Because it's symmetric, its derivative is 2 times ax, so it is equal to 2, 1, 1, 2 times x1, x2, and this is equals to 2x1 plus x2, and this one is x1 plus 2x2. So this is our gradient, and the Hessian equals A equals 2, 1, 1, 2. Now our first step is P0 is equal to minus G0, and this is equals to minus the gradient of f of x at x equals x0. So this is equals to 2 times 0.8 minus 0.25, and here is x1, which is 0.8 plus 2 times minus 0.25. So this is equals to, with a minus sign outside, so 1.6 minus 1.35, because you have a minus sign outside, minus sign, minus g, and this one here is 0.8 minus 1 minus 0.8, minus 0.5 plus 0.8, 0.3 minus 0.3. So this is our first search direction. Okay, we need to calculate P0, alpha 0 here. So alpha 0 is equal to minus 1.35, 0.3 times minus 1.35, 0.3 over minus 1.35 minus 0.3, 2, 1, 1, 2 minus 1.35 is 0.3. So we end up with this 0.413. So the first step of the conjugate gradient is x1 equals x0 plus alpha 0 p0, which is equal to 0.8 minus 0.25 plus 0.413 times minus 1.35 minus 0.3, and this is equals to 0.24, and here is minus 37. So this is our x1. Okay. So x1 is already found. So this is our first step. This is a second order system. We are supposed to get to the minimum in n equals 2, actually. So let's see this. Now we have g1 equals the gradient of f of x at x equals x1. This is equals to 2112 times 0.24 minus 0.37, and this is equals to 0.11 minus 0.5. Okay, so beta 1, it's not beta 0 anymore, so you have beta 1 is equal to g1 transpose g1 over g0 transpose g0. This is the second choice. The second choice of beta, and if you calculate this, you have 0.11 minus 0.5 times 0.11.5 over 1.35.3 times 1.35.3. So if we calculate this, we'll have 0.137, so our beta. So B1, the second conjugate direction, is equal to minus G1 plus beta 1 times P0. Okay, so this is equals to minus 0.11, 0.5 plus 0.137 times minus 1.35 minus 0.3. Okay, and this is equals to minus 2.95, minus 0.295. Minus 0.295 and 0.459. So this is our P1 direction. Okay. From this P1 direction, we have to calculate alpha 1. So alpha 1 is equal to minus 0.11 minus 0.5 times minus 0.295, 0.459 divided by minus 0.295, 0.459 times 2112 times minus 0.295, 0.459. And if we calculate this, this will be 0.807. So this is alpha 1. So the second step will be x2 equals to x1 plus alpha 1 p1. So this is equals to 0.24 minus 0.37 plus 0.807 times minus 0.295, and this is 0.459, and the end result here is 0 and 0, and this is our minimum. Oh, this is our minimizer, let's say. Yeah, so this is our mini. So this is our minimizer. X2 is this one, and if you put it in f of 0 and 0 is equal to 0. Okay, so a final word here before we end up this lecture, just to say that because we have a second order system, we only needed 2 steps to go to the minimum. So as predicted, the algorithm converges exactly to the minimum in 2 iterations. Because it is 2-dimensional quadratic function. Okay, with this we are over with the conjugate gradients, but please remember that when we calculated alphas, we needed the Hessian matrix here, so we have to look forward to see some iterative methods where we can find alpha in some different way. And as I mentioned before, the golden section or the golden section method is one good solution for this. Yeah, the golden section method is the golden section search is an excellent option or excellent search option. Okay. All right. Thank you very much for being with me in this lecture, and I hope that you will find it interesting. Thanks.